Have any questions about this or no? Anybody have any want to talk about what they've heard about Cal 2 or personal experience with Cal 2? Any advice? Anything? Anyone? You had a friend in it last semester.
He basically told me to study, and even then always struggle still, and study some more.
So study, and it's going to be a struggle.
And study some more.
And study more, yeah.
And ask you 1,000 questions.
And come to me for help. I would love to see a group of you in my office getting help. I would love for that to happen. I can't force you to do it, but we'll see. All right, so we're going to talk about inverse trig functions. So this is a, remember from Cal 1, right, that we learned how to take derivatives, and then we learned the derivatives of the 6 trig functions, right? And you should know those. Like, you should know at least the first 3, right? Derivative of sine of x is cosine of x. Derivative of cosine of x is negative sine x. Derivative tangent of x is secant squared x. Those 3 should be already wired in. Now, let's go for the other ones. Anyone know, without looking at the formula sheet, what the derivative of, let's go with cosecant first. Cosecant x? Close. Negative cosecant x cotangent x. That one's not as like off the tip of your tongue one. And I don't think in this class you have to actually know that. It's better if you do, but it's in your formula sheets, right? How about derivative of secant x? Secant x tangent x is derivative of secant x. And then derivative of cotangent x is negative cosecant squared x. Yeah, so those 3 are in your formula sheets. Just know they are, okay? So we learned the derivatives of the 6 trig functions in Cal 1. What we want to do right now is we want to remember that in pre-cal you get the 6 trig functions, but you also get their inverses, right? So we're going to remind everyone what the inverses are, what inverse functions are, do a little bit of algebra with them, and then we're going to talk about what their derivatives are. And in this discussion, we're going to do something extremely important, as my notes will say. So I'm going to blaze through this because, again, this is just like a recap of stuff you should know. What is a one-to-one function? That's college algebra stuff. It must pass the vertical and horizontal line test. If you have a function that passes both the vertical and horizontal line test, it is called a one-to-one function, and that means it has an inverse. That means there's a function that undoes that function, right? So in pre-cal, we learned that if you look at like the regular old, there's the sine function, right? In pre-cal. Is that a function, first of all? Yes, why? Passes the vertical line test. So it is a function, right? Does it have an inverse? Does that have an inverse? The red right there. Does it pass the horizontal line test? No. So we cannot define an inverse of the sine function unless we first make a domain restriction. So we have to first cut this thing off. So we can restrict it in a way that we just look at part of it. See that part right there? That part of the sine function. Notice that in that part of the sine function, it's just between negative pi over 2 and pi over 2, right? From negative pi over 2 to pi over 2, that the sine function achieves its entire range from negative 1 to 1. So if we cut the sine function off into that little region, then that piece right there is a function and it is invertible. It has an inverse because it passes the horizontal line test as well, right? So in pre-cal, that's what we do. We restrict it. And then once we restrict it, we can define the inverse function. So this is the definition of the inverse. Again, that's directly from pre-cal. And the way that I like to look at this is this. If you are in pre-cal, you take sine of an angle, right? Give me some angle. Your output is going to be a what? You take sine of an angle, your output is going to be? The angle is going to be either in degrees or in radians, right? The output is what? A number between negative 1 and 1, right? So this is a number. That's the way the sine function works. It takes on an angle, you plug an angle in, it spits a number out. So when we define the inverse function, sine inverse, the thing that goes in is the opposite of this. So you plug a number into this, right? That number must be between negative 1 and 1, and the answer is an angle. Right? So here, sine of an angle gives you a number. This number has to be between negative 1 and 1, right? But that angle can be anything, can't it? It can be any angle. It can be pi over 2. It can be 24 pi. There's no restriction on this angle. There's only a restriction on what comes out. Now, if we want to define the inverse, if you want this to actually be defined, then you have to restrict things. And the number that goes in here just has to be between negative 1 and 1. That's still the restriction for the number. But the angle now does have a restriction. The output has to be between what two values, what two angles? Negative pi over 2 and pi over 2. Inclusive, right? It can actually be that. So again, this is I'm kind of revisiting some pre-cal topics here, all right? The other notation for inverse sine, the other notation is arc sine. That's right there. That's another way to write it, right? Right there. You can write arc sine instead, and it means the same as this. How about we look at it visually? Let's do the same thing there, but visually. If you take an angle and send it through the sine function, let's say sine of x, it'll come out here a number, right? And then the inverse sine function will take that back to the angle. So it undoes it, right? But there are restrictions here, right? When we go backwards, this angle has to be, it can only come out between negative pi over 2 and pi over 2. Let's see if you truly understand that. Okay, I'm going to give you an example. This is a pre-cal problem, what I'm putting on the board right now. So as an example, I want us to find, let's do this. Let's do inverse sine of negative root 3 over 2. So this is just pre-cal, trying to get those brain cells going again. What is the inverse sine of negative root 3 over 2? So this is a number, right? This is a number. We're plugging into inverse sine, so it should spit out an angle. And that angle has to be between negative pi over 2 and pi over 2. So everyone in here is going to approach this differently. All right, I see, what's your name?
Colton.
Colton. I see Colton doing this. That's the way I do it too. I'm thinking about a unit circle right now. I'm thinking about the common angles and the common values on the unit circle. So I'm looking at this problem this way. This is the way I'm thinking about it. I'm saying to myself, sine of what angle, right, gives me negative root 3 over 2. That's the way I look at this problem. I'm saying, what angle do I plug into sine to get me that answer? And now I go to the unit circle, and I have to know something about the unit circle. I have to know, first of all, that when I'm dealing with the sine function, it's dealing with which coordinate on the unit circle, the x or the y?
Y.
The y coordinate. So this is really saying, at what angle, right, at what angle is the y coordinate this value? So where is it? What quadrant is it? Fourth quadrant. It's that right there, isn't it? Remember, there's the common angles. In that quadrant, there's the common angles, right? The one that cuts it in half, and then you've got the ones that correspond to your 30 degrees and 60 degrees, right? So this is this one right here. Do you all agree that the y coordinate there is negative root 3 over 2? Yes? So if you're not intimately connected to the unit circle at this point, it's going to be hard, right? You've got to get comfortable with the unit circle, especially in this class. We can't be trying to look it up. I mean, we want to get this thing in here as soon as possible. right, what's the answer? I need an angle. What is this angle? Good, negative pi over 3. Why did you not do that angle that goes all the way around like that? Why didn't you do that?
Because your domain restriction is only the right half of the circle.
That's right. Our domain restriction means we can only look between these two angles, which means we can only look between pi over 2, right, and negative pi over 2. We are not allowed to go all the way around and come back and give me this angle. So that's not okay, right? We want this angle right here, which is the same as 60 degrees, right? It's the same as 60 degrees, but negative. And I'm not going to use degrees, we're going to use radians because we're Cal 2 students and we use radians more than we use degrees here. So this is going to be, the angle is negative pi over 3. And so that's our answer. Okay? Questions there? You sure? It's your opportunity to ask questions. Just out of curiosity, what would the answer be if this was a positive right here instead? Positive root 3 over 2. It'd be positive pi over 3 because now we'd be saying we're looking right here now, right? Where the y coordinate is positive root 3 over 2, and that angle would be pi over 3. Okay. Let's move on. We can't spend too much time rehashing all the pre-cal stuff. So there was an example. Oh, that's the example right there. How about the one before it? Arc sine of 1. Let's do that one real quick. Arc sine of 1. So let's see if we can move through this one faster. Arc sine of 1. I'm saying to myself, okay, at what angle, and I can only look between pi over 2 and negative pi over 2, at what angle is my y-coordinate, because I'm talking about sine, is my y-coordinate 1? Straight up, right? Pi over 2. I'm done. Okay? All right, now, that's only the sine inverse, right? There's 5 other inverse functions. And they do not all have the same domain restrictions, do they? The next one we had was cosine inverse. And if you go back and look at cosine inverse, what's the domain restriction for cosine inverse? It's 0 to pi, not negative pi over 2 to pi over 2. So it's a different domain restriction. You need to be like somewhat familiar and comfortable with that as well. And then there's tangent inverse and so on and so forth, right? All right.
The tangent inverse, that doesn't include the pi over.
That's right. It's negative pi over 2 to pi over 2, not including the endpoints. We're gonna run into this in this class. So let's talk about one of those for a second. What if I asked you, what is tangent inverse of 0? My answer is an angle, right? My answer is an angle. Because anytime you have an inverse function, right? Inverse functions take numbers to angles. So this is really saying tangent of what angle gives me 0. And there's a lot of different ways to look at this as well. Anyone know what angle? At what angle the tangent function is 0?
Pi over 2?
Pi-
Is it sine over cosine?
Okay, so tangent by definition, tangent of x is sine x over cosine x, right? And you want this to be 0, don't you? So the only way that can be 0 is if what? Sine is 0, right? So this being 0 really is saying when is sine 0? And when is sine 0? So where on the unit circle, right? Is your y-coordinate 0? At 0, right? What about over here? Is your y-coordinate 0 here? Yes, but we have a domain restriction, don't we? When we're talking about tangent inverse, we can only look between negative pi over 2 and pi over 2, not including the endpoints. So the answer to this is 0. All right, let's move on. Cancellation property. So this property just says that when you put a function together with its inverse, they kill each other off. Can you all see that all right? Let me zoom that in a little bit. Let's try 150. Yeah, there we go. Right? That if you compose a function with its inverse, they kill each other off and it just spits out whatever was in there. But you have to be very careful with this, all right? Let me show you. What about if I do this? What's sine inverse of sine of pi over 4? Ooh, that's a terrible pi over 4. Well, according to the cancellation property, the answer should just be what? Pi over 4. And that is the answer. That is the answer. And the reason it's pi over 4 is because the thing we're plugging in is between negative pi over 2 and pi over 2, right? The x we're plugging in. So the answer should be pi over 4. But let me just show you, I think, a better way of doing this so that you don't ever get yourself in trouble. Just look at this first. Do you know what sine of pi over 4 is? So go to your unit circle. Pi over 4 is right here, right? Sine is the y coordinate. What's the y coordinate there? Root 2 over 2, right? Right? It's a number, right? So this is really saying sine inverse of root 2 over 2. Right? That's what that's really asking you for. And now you're saying to yourself, okay, this means sine of what angle, right, gives you root 2 over 2 with one little caveat here. You can only look on this side. You are not allowed to look over here, right? So the only way you're going to get a y coordinate of root 2 over 2 is if you're up at pi over 4, right? So the answer here is pi over 4. That's just showing you why it's true. Let's do an example where the answer does not come out like that, because I want to make sure everyone sees the difference. So let's do this one. What if I say, what's sine inverse of sine of, let's go with 3 pi over 4. A student who does not understand what's going on here is going to tell me the answer is what? 3 pi over 4. And that's going to be wrong. Okay? That's using the cancellation property without understanding the restrictions that make that property work. So what I'll do first here is I'm going to figure out this first. What is sine of 3 pi over 4? So I'm going to go here. I'm going to draw a unit circle. Where's 3 pi over 4? Which quadrant? Third quadrant? Fourth quadrant? Fifth quadrant? Eighth quadrant? Wait, there's not an eighth quadrant. Which one is it? Second quadrant. Right here. That's 3 pi over 4, right? This is pi over 4, 2 pi over 4, 3 pi over 4. What is the y coordinate here? The y coordinate is root 2 over 2. Why am I looking at the y coordinate, not the x coordinate? Because we're talking about sine, right? If this was cosine inverse, we'd be looking at the x coordinates, right? So this right here, the y coordinate at this angle, that's 3 pi over 4. So sine of 3 pi over 4, this is root 2 over 2, right? Now, what is sine inverse of root 2 over 2? Well, isn't this not the same question right here? Right? And what was our answer? Pi over 4, because we are now asking ourselves, where is the y coordinate root 2 over 2? But you are not allowed to look over here, which means you have to be here where your y coordinate is root 2 over 2. And so your answer is actually pi over 4, not 3 pi over 4. Okay. I know some of you had me for pre-cal. Do you remember doing this at all? It's been a long time, but.
So with inverse trig functions, we're always going to be restricting.
Always have to restrict them. Because remember, when you draw a sine, it fails the horizontal line test. When you draw a cosine, it fails, right? tangent, remember tangent like was just a bunch of these things that went like that? You have to restrict it or else you can't, you won't pass the horizontal line test. So all inverse trig functions must have domain restrictions. Well, the 6 trig functions from pre-cal. All right. Now that was just a recap of some of the properties of inverse functions. That's not what we're interested in though. What we're really interested in is what are the derivatives of these functions, right? Like now that we've established in pre-cal that there are inverse trig functions, what are their derivatives? Right? That's what we want to know. So let's just, I'm going to go to the next note here in a moment, but let me just put it up here. So we know this already, right? We know that if f of x, if we define a function to be sine of x, right? That's sine x. When I do my sines, I do them so fast it looks like a W. Just get used to it. It's really S-I-N-X, okay? Sine x. We know that if f of x equals sine x, we know from Cal 1, right, that the derivative of that is cosine x, right? We know that already. And we know that for the rest of them. Derivative of cosine, derivative of tangent, all that stuff. So we know this. But we don't know this. If f of x is the inverse sine function, right? We have no idea what the derivative is, unless you did this in Cal 1. If you did this in Cal 1, then you know what it is, perhaps. Does anyone remember in Cal 1, I mean, I don't know if you would remember this, how your professor showed you that this derivative is cosine? Anyone remember? A lot of times just you take it on faith, right? But you can prove it with the limit definition. You do the limit, h goes to 0, f of x plus h minus f of x over h. And what you wind up getting is a sine of x plus h, and then you use a some formula, double angle formula from some difference formula from pre-cal, and then the limit works out. And anyways, you can show it in Cal 1, you can show that this is this. But what we want to do here is try and figure out what the derivative of this is, right? Now, we can look at our formula sheets and get it, right? But how did that come, where did that come from? That's what we want to figure out. Where did that formula come from? So what I'm about to do right now is going to be very useful as we move into the later section, later into this integration idea that we're going to be doing. So first thing I'm going to do here to try and figure out what this derivative is I'm going to call this function y instead of f of x. All right? Here we go. So that's y, right? Remember, what I'm doing is I'm trying to see if I can convince you what the derivative of this is. Okay? So I'm going to let it be y. And then I'm going to write down the one thing I do know about this, and that's that cancellation property, right? I can use that in this sense. I can take sine on both sides of this equation. I can take sine of the left side and sine of the right side. Right? I can do that? That seem legal to you? Okay. Now, so long as this x, so long as that x is between negative pi over 2 and pi over 2, right? As long as that's there, and I'm not going to write it down. We're just going to say we know that that has a restriction, right? As long as that is between negative pi over 2 and pi over 2, I can now say that sine of y is what? X. Now, why did I do that? Well, I did it because even though I don't know what the derivative of this is, I do know what the derivative of sine of y is, don't I? So I've somehow rewritten the problem so that I don't have the inverse in there anymore, do I? Right? There's no inverse in there? Okay. All right, so now what I'm going to do is I'm going to use implicit differentiation, which is a technique from Cal 1. I'm going to differentiate both sides of the equation with respect to x. So I'm going to take the derivative here with respect to x on the left side. And I'm going to take the derivative with respect to x on the right side. Now again, Depending on where you're coming from in terms of your Cal 1 experience, the notation I'm using might be slightly different. It might be the same. I don't know. You'll have to kind of adapt to it. If you have any questions about it, get with me like, hey, I've never seen this notation. What is this? Come talk to me and I'll try and get things squared away with you. And while you're looking at that, I just want to back up for a second, just remind you what we're trying to find. We were trying to find f prime of x, right? That's what we were trying to find? But I turned f of x into y, didn't I? I just called it y instead. So what we're really looking for is dy dx. If I'm going to call this y, right? If I'm going to replace that with y, sorry, if I'm going to replace this thing with y, then the derivative of that would be the derivative of y with respect to x. That's what I'm trying to find, dy dx. Okay, let's do this implicit differentiation. So this step to this step is implicit. Do you all remember that from Cal 1? At least the name, implicit differentiation? Yes? Okay, we're doing implicit. Let's do the easier side first. What's the derivative of x with respect to x? 1, right? This right side is 1. Bless you. The left side's the harder one because you have to implement the chain rule, right? So what is the derivative of sine of y with respect to x? First start with sine of y. What's the derivative of sine of anything? Cosine, right? So you have cosine y. But then chain rule says times, right? Times, now you take derivative of the argument of the sine function. What is the derivative of y with respect to x? Dy dx, which is what we were solving for, so it's good we're seeing it here. So we have this dy dx here. Right? And that's what we're trying to solve for? So I'm going to isolate it now. I'm going to get it by itself on one side of the equation. So to do that, let me come over here and do it. So to do that, I'm going to divide both sides by cosine y. I get 1 over cosine y, which, what's the reciprocal of cosine? Secant. So this is secant y. So my answer is secant y. Remember, we were trying to find what the derivative of inverse sine of x was, right? And what is our answer? Secant y. Wait a minute, hold on. Our function that we started with was a function of x, right? And our answer is a function of y, isn't it? Wouldn't it be better if we could get our answer to be a function of x as well? Right? So even though that is correct, we're going to go one more additional step to try and turn this into a function of x instead of a function of y. Does anyone have any questions up to this point, though? All right, the next step is the big step, the step that is going to be very useful as we proceed in this class. I'm now going to make what is called a reference triangle. This is going to be a visual aid that's going to help me figure out what secant of y is in terms of x. I'm going to try and transform this into a function of x. So I'm going to draw a right triangle, and I'm going to base that triangle on some information over here. And what I'm going to do is go to where I first had that sine function appear, sine of y, right? Sine of y is x. I'm going to use that information right now. I'm going to write down over here. I know that sine of y must be x, right? I would like to know what secant of y is, but in terms of x, not in terms of y. So to figure this out, I'm going to draw a right triangle. The angle that I'm plugging in here is y, isn't it? Sine of y. Y is the angle. I'm going to label this angle y. And then I'm going to look at this x right here on the right-hand side as a fraction. I'm going to look at it as being x over 1. And I'm going to recall from pre-cal that sine, that whole SOHCAHTOA thing, right, is opposite over adjacent, isn't it? Opposite over adjacent. That's what that represent. So I turned the x into an x over 1 on purpose so that it looked like a fraction, like a ratio. So I could call the x the opposite and the 1 the adjacent. And I'm going to label my triangle that way. The angle, or the side opposite of y is here. That's x, and then this side is 1. Yes? Oh, why did I put opposite? Oh, sorry. Did I say hypotenuse?
No, you said adjacent.
I said adjacent, thank you. Okay. Day one. No, I'm glad you said something. Yeah, if you see something obvious like that. I did it right on the triangle, didn't I? Okay. Opposite over hypotenuse. SOHCAHTOA, right? So why have I done this? This is a visual, this is a visual representation of that equation, right? This is a visual representation of that. The reason I did that is because I would like to see what this is, right? Secant of y. See, the angle here is y, and that's the same angle as that in that triangle. So I just need to figure out what secant of y would be now. What's the definition of secant of y? Well, in terms of SOHCAHTOA. Well, this is the reciprocal of cosine, right? What's cosine? Adjacent over hypotenuse. So this should be hypotenuse over adjacent, right? This should be hypotenuse over adjacent. Do I know the hypotenuse? Yes. Do I know the adjacent? Not directly, right? But could you solve for this adjacent side? Sure. Let's call that side A. Let's call that side A. And let's solve for A. And I'm going to use Pythagorean, right? I know that A squared plus x squared must equal 1 squared. That's just a squared plus b squared equals c squared, that thing. And now solve that for A. So subtract x squared on both sides. The 1 squared becomes 1. And then take a square root. A is square root of 1 minus x squared. And that should technically be plus or minus, right, for that A? Should be plus or minus because I took a square root. But I'm only going to use the positive because I'm talking about this side of this triangle. And within the domain restrictions of the inverse, I'm on the right-hand side. I'm not on the left. So right, I'm between pi over 2 and negative pi over 2. So everything should be positive on that side. So that's what A is, right? So that's this side is root 1 minus x squared. And so now I can give you my final answer here. dy dx is hypotenuse 1 over adjacent square root of 1 minus x squared. That's the derivative of inverse sine. Now this is on your formula sheets as well. A couple of reasons why. Remember right here, when we were doing the inverse, right, we have to be between negative pi over 2 and pi over 2. Can't be